Hello and welcome to 20th lecture of course on data-enabled tribological engineering from experiments to predictive model. Topic of this lecture is Introduction to Data-Enabled Engineering. So we want to first differentiate what is the really difference between the data-driven engineering and data-enabled engineering. Often there is a confusion or confusion arise because of the very similar terminology. We say data-enabled engineering, which is the topic of the present lecture. It is a method of improving and supporting engineering processes. It's basically it helps to make a decision. So engineer can access the data and use to make a better judgment. Whatever the decision we take, it needs to depend on some facts, some data, some knowledge, some information. And that is what engineers are really required to access those data, those information. Reason being, once we have those data, then ambiguity will be much lesser, work will be faster. In the situation, we need to focus on integrating data into engineering workflow. That means whatever we do, it should have some supporting data. We are taking some judgment, we need to have some sort of information available that why we are taking this decision. While data may not always be primarily determinant of engineering decision, or we may use our intuitive thinking, we may use some other judgment, thinking something different. Not necessary in every case the data will be a completely giving a decision. However, in data-driven engineering, decision need to be based on the data. While in data-enabled engineering, decision may not be based on the data. Here the engineering is coming, we have some history dependence, we have some theory, so we have additional knowledge or we have a tacit knowledge also. So in case of the data enabled engineering, those informations also are required. While in data driven engineering, we require only data. So that's why we assume that first we will go with the data enabled engineering. We will make a good model, robust model, then we'll shift to the data driven engineering. So that's why we say now it serves to enhance the understanding of the problem, whatever the data we are getting. It really helps to understand the problem, refine the methodology, whatever methods we were choosing, it can be to some extent be modified also based on available information, and then we will be able to take more informed decision. So this data enabled engineering will be covered in lecture 20 to 22nd, that means this present lecture and 21st lecture and 22nd lecture. Towards the end of the course, again we will cover this data enabled engineering, lecture 33 to 36. So whatever I mentioned, I just want to give some sort of brief what we have done earlier. You refer the lecture 14, we did a coating selection. In coating selection, we assume there are 5 coatings available at manufacturing facilities. For the 5 coatings are available and their 4 properties are available to us. Now these are the data which are coming from the literature. We have not done any experiments on this. So based on the 4 factor and 5 coating, we wanted to make a decision. Then we use our thinking or digit logic method to compare the property 1 and 2, that's the hardness versus Young's modulus, property 1 and 3, hardness and thermal expansion, then 1 versus 4, that means hardness versus cost, and then we introduce some dummy parameter. So this is where we have taken decision with some other method also. Here we don't have a data, we have just compare. If there's some sort of intuition or some sort of expertization, or we say that application oriented information also was involved. Based on that, we selected a coating, which coating will be the best coating. Again, if we have many data and we do not know exactly everything, we'll prefer to choose maybe say 5 selected 10 top 10 selected materials or manufacturing processes. Then we will perform the experiment, and based on that whatever the data comes, we will be implementing those data, and then we will move to the data driven approach. Let me take another example. We refer the lecture 19. We, based on the data, we say that even though we have a 4 factors and each factor has a 3 level and full factorial design requires 81 experiments. However, the established literature says that if you go with L9 Taguchi design, that will give a good results. So we analyze those things. We use L9 orthogonal array, and then we found that this orthogonal array has a degree of freedom 8. However, we are having a 4 factors, or we say the 4 powders, each with the 3 level, 0.2%, 0.4%. That itself requires 8 degree of freedom. That means L9 can give only the consideration of the main factor. Interaction will not be accounted. So we analyze using our decision or our intuition or our information, and then we say that we opt for L18 as a orthogonal array compared to the L9, because L9 is not giving all the information. So here we use our engineering decision by analyzing the data. In data driven engineering, most of the information will be provided to software, and the software will take its own decision. Or maybe we say we are trying to convert it in automation. So if it is more and more automation, we are moving to the data driven engineering. Of course, in that machine learning will be used extensively. Let me put in my words. We say data driven engineering emphasizes extensive use of data to inform engineering decision making and problem solving. Engineering decisions often rely on data driven trend patterns insight, making data focal point of the decision. So everything we have a data and we are not taking anything else. So data plays a crucial role in engineering decision making and provides essential guidance also. So all the guidance are coming from data itself. And data driven engineering involves extracting valuable insights from a data through application of data centric techniques. Now here we are using the machine learning and advanced analytics. So that means if you are going to use artificial intelligence, or we are giving some sort of automation, then this kind of approach will be good. However, in my view, first we start with a data enabled engineering. We make a very good models and then move to the data driven engineering where automation can happen. So it helps to automation. This approach will be covered from lecture 23 to 32. And what are those lectures? Lecture 23 is the introduction of machine learning algorithm. Lecture 24 is a regression and classification algorithm for tribological modeling. We really require a relation, so that's why the regression analysis is done. We will be covering deep learning for the tribological application in lecture 25th, data driven model for the friction prediction, data driven model for the wear prediction, data driven model for lubricant optimization, data driven model for tribofilm formation, data driven model for tribocorrosion prediction. Prediction of the coating and surface treatment is again a data driven approach. Coming to the 32 lecture, optimization of surface engineering processes using the machine learning. So all these are the data driven approaches. Now if I want to summarize in the words, we say we will be using data analytics to extract the meaningful information from a raw data. We may require to fuse the data or the data fusion. That means we will be combining the simulation models, we will be developing some sort of predictive models, and then we will be using the real world data to correct it to suit the real situation. That will improve the accuracy of the prediction and optimize the system performance. We may involve the digitization. Again, the digitization has been explained in literature in various ways. In my view, we will be using some sort of graphs and then maybe say images and converting to the digital form, so that we can really remove the noise. We make a signal to noise ratio on the higher side. For that purpose, we really require a digitization. The digitization and data-driven methodologies will be used together, a combined manner. That's what has been mentioned to automate and then increase efficiency. We will be also doing a predictive model because we will be requiring what is the remaining useful life of the component. So the predictive modeling is important. So that's why we'll be doing a construction and verification of the models. Of course, with a lesser number of experiments, the way which we have learned in lecture 19, and we say the design of experiments. So we'll be using design of experiments very effective manner. We will be trying to do optimization but based on the data examination. It's not we have some model available and we will do the optimization. We know very well that most of the models which are available, including the finite element models or CFD models, they incorporate some sort of assumption, and those assumptions may become invalid in the newer situation or when we are dealing with some other application. So in the situation, we will not be able to utilize those models. However, that can provide initial start, or maybe say in a starting purpose, we can get some sort of a model and which needs to be modified. So what we will do, that we say examination of the data to identify bottlenecks, trends and irregularities. If you are able to judge what are the bottlenecks and why the trend is not being followed, and what are the irregularities or why irregularities are coming, why the noise parameters are increasing, based on that we can optimize in better manner. So utilization of digitized curve, as I mentioned, that most of the curves, engineering curves are available in the literature. We want to digitize and then we will be including in optimization process. We learned something about the statistical analysis in a lecture 19. We will be improving that by adding the more the data in that. So we will say at a statistical analysis will be involved, and then if we are there are some possible dangers of the failure of the system, those should be predicted. So if we can use it for the maintenance strategy, this complete data. So we will be using lecture 23 to the 32, incorporating the data handling in a better manner. We will try to synergize data handling with the machine learning and then give the better results. If I try to explain in my other words, we say in my view, full potential of machine learning can be understood by properly handling the data. One of the biggest problem with the tribological data, tables and graphs is finding the right factors. We have a number of tables, we have a number of even the algorithms available. I will be showing in next 3 slides about those. But how do we predict, how do we find the right variable? Because many times we do not have a complete information. So what we say, that availability of the vast data, that too in non-standard format, can be standardized using the ML or machine learning, so that algorithm converges effectively. Many times we make algorithm, it doesn't converge at all. So to provide a better initial approximation and go in much more effective manner, we will be requiring this. Improving the model accuracy and reducing the curse of dimensionality. Will be telling about that, what is the curse of dimensionality. We have a many dimension, like some people say that we are choosing 44 factors. How do we deal with the 44 factors? Actually, we will try to reduce using the PCA of the machine learning, so that the dimensionally curves can be reduced and we get a more useful data. You see, in machine learning, we partition whatever the available data in a training set, validation test, and test set. And this division, it really helps us. So what we do in this way, the model gets tested in variety of the situation, which helps it to make it a flexible model. That means we do not have a rigid model, and we have some sort of flexibility, and then we can improve also based on the future data, fresh data, available data also. So we say that by adjusting the model hyperparameters, one can improve the performance of the model and prevent it from being overfit or underfit. That will be explained in the next lecture, what is the meaning of the overfit and underfit. So in my view, I say machine learning is an ongoing process. It doesn't stop. Earlier, all other classical method, they give one method and stop there. However, machine learning is continuously changing and it is able to incorporate the newer data. So what we say, it is crucial to continuously monitor performance of the model whatever we have made, and keep this model more relevant with the newer data or a newer situation, newer application, newer data must be added in machine algorithms also. In this situation, what we say, the machine learning accepts the future data and provides some sort of feedback loop for the reinforcement learning, which is another machine learning classification. We'll be discussing those in the future lectures. Now, I'm just trying to show the data availability in our literature. You can see here the title say the numerical tribology information system. Tribology principles in an expert system. Earlier, people used to think about expert system, and I feel expert system is basically whatever we do coding, it will give some decision. Now, if you are providing a newer data, newer application, newer format, that may not be able to get into the expert system, or expert system will not be valid for that. So that's why we are trying to bring this machine learning algorithms. Here you can see here abrasion resistant material expert system, where expert system for the unlubricated tribal system, numerical data bank, and tribological behavior of the polymers. So there are a number of database available in literature. It's not that we are doing first time or we are learning first time. These are already available. So we should be able to utilize this data in a proper manner. That's what our aim of this course is, that we should learn. We learn from a history what people have done, and then how effectively utilize those data for our purpose. So here we can see here that the coating selection expert system, surface coating selection expert system, numerical and tribological database. Again, these all database are basically on for the one organization or one division. They have not made it open. So we are not able to access all the data, all expert system. However, whatever has been published in literature, we can utilize those systems. However, if you are able to get information, I have given complete information. ACTIS has been given a computerized tribological information system. Another is the PERCEPT, the name of the tribological expert system developed in Netherlands. ARMES, this abrasion resistant material, that's what has been given. Tribolog is something, name of the tribology database developed in France. Tribodata, name of the tribology database developed in Germany. Tribesal is the name of the tribological system in developed in Netherlands and UK. So these are the similar system has been developed now. This is a Tribocolite, the name of the tribology system developed in again in Germany. So these are the names which are available in literature. The question comes, what is a robust solution? Reason being, whatever the expert system people have done, they have done for their own or for their lab, for their company. It's not available to common society. And our course is aimed to give this information to the society so that they can take a decision. So we are trying to educate, we are trying to provide information systematic manner. So the future they can really develop and they enhance or they can provide a better solution to the society. And we are aiming for the robust solution. If you look at the data, even one lab data will be different than other lab. So which material should be utilized? And now problem comes with the decision making, because they don't explain complete situation. They explain only few factors which may not be correct to define the tribological system. Let's take another example. There is another paper which is published in 2008. What they did, they developed a database for tribological system or tribological property for the DLC. And my previous lecture, maybe say lecture 14 and 15, I mentioned the DLC, and I say the DLC is not a one coating, it has a several coatings. So what is the purpose of this paper is they wanted to gather and compare data on the DLC coatings only, and then they wanted to go ahead with the coating selection based on the requirement, and then gain a new site through data analysis. They assigned 49 attribute to that. So 49 attribute variables. Now material description, coating deposition parameter, test specimen, test parameter, test outcome, there are some sort of class in that. So there are many parameters or many variables. Also, they included their own data, and then they also covered 800 coatings which have been documented in the literature. So when we try to go ahead with this kind of approach, naturally there is a lot of abnormality, or we say results will vary from one lab to other lab. Now, how to really denoise this? So that's important. Because they also mentioned that they discovered the absence of uniform reporting standard among the scientists, and then that's why we don't have really a good data set available to us. Of course, and they also mentioned that most of the time the test in which they have been done, then the material been tested, they are not defined properly. Coefficient of friction itself ranges from a 0.05 to zero point 0.2. That means it's almost 4 times increase or 4 times variation. Naturally, this kind of data are available, and we should be able to utilize for our situation by going through systematic manner, and then finally top 10, top 15 material or top 18 material, we should be, or the method should be selected which should be performed in our lab, or maybe to get more knowledge about that, so that we, whenever we take a decision, it's not based on only on literature, but what has happened in recent time, when the particularly the manufacturing processes are continuously changing, material compositions are changing, particle sizes are changing, so those also can be accounted. So history dependence is a required, what is available in literature, what is available in present, and then how it will improve, and what kind of the cost economics will come because of that. That should be accounted properly. So there is another paper in June 2021 published. They try to give a new method, which is triboinformatics, to go ahead with the concept, architecture, and a case study. The paper was published in the Friction, and then they provide a notion of the triboinformatics. The major reason is the interconnected activities that involves a tribology, standard, and a database, and utilization of information technology to gather, categorize, store, retrieve, analyze, and distribute tribological information. So that the overall aim is good. In this case, they are trying to gather, they are trying to categorize data, they are trying to store, and then they are trying to provide some sort of a distribution information of the tribology. So that is very good in the way, but it is not really available in the full form to the common people. In this case, tribology system consists of various components. Again, they face a more problem. Reason being that when they are moving from coating to lubrication, the data changes significantly, and then usefulness of the whatever the data they have collected, it becomes a lesser. It is not widely used. So better we take overall good framework and then choose whatever the we want and apply for that. So if instead of going for only the collection of the data, we look at how the data will be utilized for our application, and that we try to get a solution for that. And overall, this course is made from that angle. We learn first tribology, learn about the data enabled engineering, then learn about the data driven engineering, and finally find out with the data enabled engineering. I'm giving another one example that the paper was published in 2019. It's a fleet-wide data-enabled reliability improvement of wind turbine. So this is a kind of very close match what we are trying to do in this course. And then what they develop, they said they develop a control strategy for the wind farms. Of course, this is what I say, the reinforcement learning algorithm, which will be dealt in the future lecture. So they use data set from a history, and then they try to explore what are the failure modes of wind turbine, and then they use another data set which are that they were getting directly from a wind farm. So history dependence and what is available in literature, use those data, get number of sensors, and then use those sensors to acquire the data, and then try to compare to overall achieve to develop a model which could learn from actual wind farm data and incorporate past failure of the wind turbine. This creates a model which is more specific to the wind farm. So this is basically application oriented. In this case, it has been utilized only for wind farm. That means we don't really require a data for almost everything. Whatever the system we are taking, whatever the application we are taking, what are the relevant data available to that? And then use a sensor suite or sensor system with a actual system, and then get a results and modify the model and using the machine learning or utilizing the reinforcement learning algorithm. So that to do that way. Now, in this case, author have claimed that they came up with a thinking about emergency brake control, which doesn't shut the turbine immediately, but gradually bringing turbine to stop in a cascading manner. Of course, they have given a strategy to reduce the wear rate of the gearbox and other subsystem and allow turbine to operate for the longer, enhance the service life by extracting uh, as much energy as possible. So maximizing of energy extraction, minimizing of wear, and then they use existing data or history of the wind turbine failures, and then they were getting the data directly from wind turbine, and they try to implement a new control strategy, giving more control to the brake and then in the manner so the turbine is gradually stopped one by one in cascading manner, so that overall wear rate comes down significantly and then energy extraction is maximum. So this kind of application will be useful so that wear rate is reduced, energy output is increased in the manner. And that's why we say whenever we try to go ahead with anything, look at what are the failure modes and how the component are failed, so that similar kind of the failure should not happen. And we do better and better condition monitoring and then access the data so that overall results are in favor. It is always giving a minimum wear and minimum friction and very long life. Let's talk about now again data enabled engineering. Say what are the key components in data enabled engineering. We say first is the integration of the data in engineering itself. So what is our focus? To collect, analyze and leverage data, better use of the data to enhance the design, decision making and drive system performance. So that's the main aim. We say try to integrate the data, collect the data, analyze the data, leveraging the data so that design can be improved, decision making can be improved, performance of tribal system can be improved in this case. So in this case we say that it encompasses various data source. It can be design data book, it can be historical record, it can provide a simulation. Sometimes we have a CFD solution available, and but everybody cannot understand. So we try to do some sort of normalization and we try to give some sort of curve fit equation. Those curve fit equation can be utilized, but of course we need to give a one or two parameter which should have some flexibility when we do experiments or perform experiment or get a data. Those factors can be changed. So that's what we get a use of the simulation also, experimental measurement and operational data. So this need to be integrated in a comprehensive manner so that we understand the engineering system, we understand the problem in a better manner. This will be detailed in lecture 21 and 22. We say data collection and preprocessing, feature extraction and selection. Of course, most of the time this is used in a condition monitoring. We say engine health management is one of the company's method they have done. They use 25 sensors and then they measure the pressure, measure the temperature, vibration, shaft, including the temperature is there, and addition they go ahead with the humidity measurement also, so that they are continuously getting the record of the data, and whichever parameter goes out of the bond, naturally they will try to monitor the system. And most of the turbine system also incorporate this kind of health management. In addition, we need to look at the cutting edge technology, because everyday technology is improving. We already know the Internet of the Things. Now we have a sensor, much cheaper sensor, and then they have a better communication in these days. And these sensor can be directly embedded in systems also. They can the embedded in object. They can embed it in the production system and the processes also, so that overall management of the operating system can be improved, or we say operational efficiency can be improved in the manner. So IoT can be utilized as a cutting edge technology in this case. So we say utilize advanced sensor technologies, data acquisition system or methods, and computational power, data accessing, processing, those things will also come in this case. What is the emphasis? That our emphasis is a high quality and diverse data. This is a very important that we need to have a different kind of data available so that we get a complete range. Should not happen only for the one operating condition, two operating condition we are getting data. Another one is that inside of the tribological phenomena, which we have already covered in lecture 1 to 16, those were completely on the tribology, so that we explore the tribological phenomena, employ whatever the models that are available, methods which are available, so that overall we get a better and better, deeper understanding. So in this case, what is our aim? Aim is to devise more efficient solution by leveraging the available knowledge and insight which you are getting plus data. So we are integrating data, we are integrating cutting edge technology, we are integrating our tribological knowledge which we have learned from lecture 1 to 16. Then we need to go ahead with this kind of regression model or predictive models. We say creation of the predictive model. So utilize experimental measurement to develop highly accurate and reliable predictive model. So we get a model first, and then we do experiments, and then we improve the model which we are getting from tribological knowledge or available other data knowledge, or and then trying to improve with the cutting edge technologies output, or maybe sensor which is being delivering data to us. Finally, this needs to come a visualization, because the representation has to come what we are doing. A common man will not be able to understand, a non-technical person will not be able to understand. So we need to present in a better form, and that all together integration, cutting, insight, creation of predictive model and visualization will come into the data enabled engineering, and this is what we really require. Now, what is it conventional tribology which we have done in lecture 1 to 16, and then why we want the way forward and the better method? We say there are limitation of the conventional tribology, but we say we are able to utilize tribological theories. They provide a fundamental concept, we understood many things, but overall the model which come out, they are oversimplified. We take a lot of assumption and then simplify those models. Then whatever the experimental testing is been done, we record. Of course, we follow the some standard as such, but again this standard we follow and we get some model to control the wear test and friction, and then we get those kind of results. Now but suppose we really require a next step, we want to control the temperature also, we want to control humidity also, then what will happen? Or we want to change some operating condition, then what will happen? So whatever we are doing here, they are limited, they are not extensive. So whenever we find an application, one factor or two factor or three factors are changing, better we come up with a better model with a new form of the tribology or a modified form of the tribology. So we will see in this, based on this, generally we go ahead with empirical models which are again having a limited range, and we cannot go ahead with performing numerous experiments. In lecture 19 we say that we should have some sort of regression analysis or regression method which comes from ANOVA, which is not coming out, which is giving only the linear relationship. But we need to perform experiment what really theoretically we are getting optimized results based on the experiment which we already performed. Reason being, we cannot go for the numerous experiment, like we mentioned the 9 experiment compared to 81 experiment, and then we realize 9 experiments are not sufficient, we should move to 18 experiment, and this 9 experiment will be a part of this one. That means we are going at the 9 plus 9, we are not rejecting anything. So this is very sequential manner we need to improve our results, and then we cannot go directly on 81, but whatever we do initially we learn and then modify, again do experiment, again learn and modify, and that's what we are saying that we should adopt this kind of approach compared to the conventional tribology. So that's why we say that we should go ahead with a data enabled tribology or data enabled engineering. But we say that D involves a sophisticated data interpretation approach, utilize ML and advanced analytics, which is important, and then thorough examination of the data sets also. So here when we have a lot of data, we have algorithms available to uh, find out whether those data are correct data or some sort of the noise is there and we need to reject. I'll show you the couple of examples in this lecture also. Optimize the design process and the systems by extracting pattern, correlation, predictive indicator. So this is where we need to really focus. And in addition, sometime we did not realize that there is a problem when we are trying to integrate all this using the data enable engineering approach. Then we realize there is a gap, there is some knowledge which is we don't have, and again we need to formulate the problem, experiment it, or maybe do some sort of theoretical calculation and perform experiment, improve it, so that overall better decision can be made. So this is a what a continuous process, and then as I mentioned earlier, the machine learning itself is an ongoing process. It doesn't stop. So whatever improvement we have done, tomorrow improvement should be on a higher side, or there should be delta improvement on that too. So if I try to summarize what I mentioned, we say that we want proficient in information processing, we want predictive analytics, we want to go ahead with optimization strategies. When we are going ahead with the information systems, we generally collect, analyze, and drive the actionable insight. What are we trying to do? And then we already have some domain knowledge, and we are trying to go ahead with a regression model based on that domain knowledge. Maybe inaccurate initially, but once we get some information and we are able to analyze, then we continuously move on. So that's why I say first to get it and then think about what are the continuous improvement or possibilities of the improvement. Using the predictive analytics, we say we try to utilize the historical data whatever we available, then we use advanced algorithm what we have seen in these days, and then quite possible advanced algorithm can really come up with some pattern which earlier we were not knowing. So this is what we say, advanced algorithm to reveal unseen patterns, and then try to find out what are the complex relationships. As I mentioned in the last lecture 19, we have a parameter, b parameter, c parameter, d parameter. We may not know what will be the effect of A into B, B into C, and C into D. We need to really understand. So the complex interaction is also possible. Instead of going with a linear relation, we think about a non-linear relation and come up with a complex and the models, so that overall results can be improved, or there is a possibility of continuous improvement. So this is a very important thing. Then comes to the optimization. We know that we can be only competitive when we are trying to maximize the returns, and we can be competitive when we are minimizing the risk, and then we need to enhance efficiency. So these are the important from engineering point of view: maximize the returns, minimize the risk, enhance efficiency, of course through data collection, data processing, so that informed decisions are better to us. And then for that purpose we do a real-time monitoring, and then we apply also predictive maintenance. Of course here we require artificial intelligence and machine learning. So this is what we say, that we find there are some drawbacks in tribology or conventional tribological method, and we need to improve the system. And this complete three lines: proficient in information processing, using the predictive analytics, adopting the optimization strategy. They are going for the future, obviously, that we want the way forward, and the improvement in tribological methods. Let me take one case study. I'm giving only one slide on that. This is a triboinformatic modeling of dry friction and wear of aluminum based alloy using machine learning algorithm, which was published in 2021. What they are trying to do, they are using some sort of regression models. You can see here, but I believe that this regression models cannot be useful. One is that this is a linear relation. Second thing is r square itself is a very low value. We cannot go with such a low value. And second thing is that in an earlier lecture, as I mentioned, we need to go with a multi-objective optimization. So I talked about that in lecture 10 and lecture 19 also, that I'm trying to show in the same thing here. Now you can see here aluminum 7075, that's a coefficient of friction. It gives a 0.49 coefficient of friction, but it gives a very low wear rate. So one material, very bad in friction but very good in wear. Now coming to the second one, here you can see aluminum 6061. Here the coefficient of friction is a 0.265, but wear rate has increased. So which material should be selected? Coming to the third material, say AI356. In this case, wear rate is on a slightly higher side compared to 7075, but friction is slightly lower compared to the AI7075. So here it was a 0.49, here it is a zero point 0.4. So these are the different, like we are getting good results in friction or getting good results in wear. So everywhere we find that there is a difference in friction behavior and behavior, but we want both. They collected data from literature, and they allotted this for the, as I mentioned, machine learning. Go ahead with the training and validation and testing. So this is that they have incorporated 344 data for the training, then 115 for the validation, 153 for the testing purpose. So in this situation, generally we go ahead with the 70, 20 and 10. However, they have used a slightly different approach to get a data. 70% is basically we go for the training, 20% will require for validation, and 10% for the final testing, or sometimes we say that reinforcement also, that we require a next level data, not this data. However, as I say, the R square factor is on a very bad side, and then we need to improve this factor. This is not really giving good results. If it gives some zero point 0.9 onward, then it makes sense. Otherwise, it is not really giving the good results. So we can say that there are several challenges. First, major challenge which I realize also is interdisciplinary collaboration. We really required effective collaboration among the engineers, data scientists, domain experts also, even the people who are experimenting, how they are doing it, because slight change in experiment itself, the results will be different. So that overall, if there is a strong collaboration, then only the maximum benefits will come. So this is a good for the company where there are 50 engineers, 100 engineers. Particularly for academician, individual labs is a little difficult. We need to also apply PCA kind of tools, even though PCA itself has a number of drawbacks. We say this is basically to reduce the dimension. Now instead of going have the 15 factors which are available in one data set, okay, now I say no, I don't have control on that, so we need to analyze it, and then we see quite possible the four factors or five factor overall contribution is a 95%, and remaining 10 factors the contribution is on 5%. So in this situation PCA will help us. And then how it helps? The performing PCA involves using covariance and correlation matrix to identify adaptive new variables. So this five factors may turn out to be new variables as such from a data set, and then they try to incorporate all the results, and then it cannot be coming directly from a data set. So again, first is that identifying for 15 factors, then doing PCA, then figuring out what are the factors and what is the contribution. As I mentioned, the 5% and the 5 factors are giving 95% contribution, 10 factors are giving only 5% of contribution. So we can neglect it, but we need to again show the results, and that's why we say that we need to go ahead the new variables which may not be exactly the same variable which we adopted, but slightly different manner. So that need to be really identify, and identifying those and replotting those is really a challenge also. Coming to the standardization of variable, if you look at the data have been plotted and then acquired very different manner. So we don't have a standardized method as such. However, for that purpose, again we can go ahead with standardization, so that we can go ahead with the zero mean and the unit variance. So all the data should have a unit variance for the standardization. Again, converting this kind of data or standardization variable is also not easy. So we really required a first accessing the data, then converting into the standardized format, and then replotting it also. This is what we are going to cover in the next slide. Digitization of established cover. Most of the books, most of the handbooks, most of the publication, they provide a curves to us. They don't provide a complete tabular form details. And the curve we will get and we will try to digitize those curves. So if we say the in field of the tribological graphical representations are the common, and challenges lie in the digitization process. We will have algorithms and then we can do digitization, but is an additional process to be done. And converting analog to graphic or graphical representation to digital form becomes essential for us, which will be explained in the next slide. And particularly this is required because we are working on machine learning algorithms and we really require the data for that. And last, what we have mentioned that 23rd to 32 lecture, we will be covering data driven approach. That means we nearly require to implement data driven approach, making decision, gaining insight from a data analysis. This is important. We say uncovering hidden relationship which were not known earlier. People have been doing experiment, they know some variables, but what is the relation between the variables that may not be known to them? And trends in the large database require application of statistical methods which will be required, which will be involved, and machine learning itself has a base on statistical methods. This is what we really required to handle the challenges when we want this course to be effectively running and effectively giving insight about the system and how do we analyze the data properly. Now, as I mentioned, I will be giving a few slides on the digitization. We are saying that in this case, we have a software Origin 2020B which we have downloaded and it is available, freely available. Then that's what we do in this situation. We want to digitize the image. It can be graphical, it can be anything. Image digitization, what we can do, that process of transforming data or graphical representation to digital one, and we are using the software Origin. Once you download, you open the file and then you can really open the file, image file in this situation. Now here, because image can be at the different levels, so initially we really require some sort of calibration. So what is that? We do allocate the some sort of reference points. Now suppose there is a graph available in some parameters. We say p1 parameter p1 and parameter p2 and this kind of curve. So if I have a given getting some data available to us, then or maybe we know this is available to the 1, this is available to the 2, this is available to 3, this is available to 4, 5 something. So we try to come up with that kind of thing, locate the reference points and with a specified length and dimensions, whatever the dimension we know, we can go ahead with the square form or maybe as I say 1, 2, 3, 4, 5. We measure based on that and we calibrate the curve. So the overall results can be presented in real data which have been utilized for P1 and P2 curve. Then we try, once we have done a calibration of 4 data, 5 data, 10 data, then we trace the image, so that whole digitization process starts. That means initially we need to do some sort of manual work and then a system or software will do its own and then it will extract the data. We say once the characteristics have been traced, convert into numerical data point. Depending on the complexity of data, technology or maybe digitize it or data extraction can be utilized. So in this case we are going to show the xy on the plot in next slide, and then next to next slide in this, not in this. Here what we are saying that whatever the data being collected, we can use a curve fitting method in either in Excel 365 or the MATLAB which we have in the labs. So you can use Excel or MATLAB to verify it. Now only thing point comes in this case is R squared value. If R squared value is a bad, then it is not correct. And one of the slide, earlier slide or 19 slide, I showed that R square value was 0.3416, 0.66. That's not correct. We really required a better value of this. So that's why we say that when we are doing this kind of Excel or MATLAB, this R square value, which is also known as the coefficient of determination, should have at least 0.9 as a value. Point lesser than 0.9, generally we assume it's not good curve fit. It's not giving the representation, right representation in this case. And then in this case, so it is the same thing in the MATLAB which we have done. Now these are the curves which we are saying that I'm adopting, taking from one literature published in 2018. Here they have found the corrosion rate of aluminum 7075 in H2SO4, sulfuric acid and HCl. You can see the corrosion rate has been given, and then this 0%, 2%, 4% hybrid value has been given as a nanoparticles which have been given in aluminum powder. Now this clearly indicates when we are using the equal value of aluminum oxide and SiC powder, then becomes hybrid, and that gives a low corrosion rate even in case of the sulfuric acid as well as in case of HCl. While a 2% individual is not giving a lesser value, in fact is giving more value, 4% is also giving higher value compared to 0%. So this is what we wanted to digitize and replot, and that has been shown over here. We have digitized using the curve, and here it has been given the R squared value indicates how well a regression model fits the collected data. This value should vary from 0 to 1. Value of 0 implies that the dependent variable cannot be explained by independent variable. That means y, if I am assuming this is a y and this is x, and then the 0 value means y itself is not a function of x itself. There is no dependence in this. While value of 1 shows that independent variable completely can explain all the variations into the dependent variable. That means if it is a r square equal to 1, then there is a strong correlation between x and y, and then we should go ahead with that relation itself. Now here we have digitized it, and then we found is a polynomial curve, and this x square is clearly indicated. Now it's a very 0%, 2%, 4 and the 4% or hybrid. In all the cases, you can see here the R square factor is 0.9 plus. You can see here 0.999, 0.9995, and all has been done, so it can be digitized. Once we have this digitization, after that we can get 100 data, 1000 data from this graph itself. However, in this case also has been shown that this corrosion rate in HCl is almost 50% compared to the sulfuric acid. Obviously, then sulfuric acid corrosion rate will be much faster, but on a higher rate compared to the HCl. Now, this is a similar kind of thing, and HCl has been again shown. A previous slide was on sulfuric acid. Now in this case it has been shown in HCl, and here also the similar polynomial graph has been shown 0.99, 0.99, 0.99, 0.98. So results have been similar manner. The curve has been digitized and to the get a results. So now this is an Excel sheet and this is a MATLAB. You can use Excel or you can use a MATLAB both. However, we are doing a coding mostly in a MATLAB, so we prefer to use a MATLAB. Now I picked up this slide from a lecture 16 where the corrosion testing results were presented using the eddy current testing and such, and then you can see here that they have coated and they have uncoated value, uncoated value, and then they have also used a fit line, curve fit lines. You can see here the data have been given to us. Now if these data have been given, that means 4 data for uncoated case, 3 data for the coated case, I can use a digitization, and that has been shown a digitization. In this case you can see here this has been given as a log plot. So when we are doing a digitization and we are replotting it, then only we are realizing what are the real characteristics. We know the with exposure time PV value is changing, but what is a really curve, what kind of curve has been defined there, that doesn't give immediate intimation and immediate feeling about that. However, when we go with this kind of curve fit method, regression method, then we are able to understand what kind of relation has been established and why they have been done. Is it the logarithmic, is it exponential, or is it polynomial? How do we go ahead? And this will really help us in machine learning to get a results. Not only this, sometime maybe get outliers also, that regression analysis, and now here and there, and then suddenly one data is coming. So that's a outlier, and we can identify those outliers, and we can say that we really require more number of experiments, because this 3 experiment, 4 experiment, they are not giving sufficient results, or we should look at some other literature which has a more number of points. Once that comes out, then only the results will be more favorable to us. Similar example here, again again eddy current test. Here another parameter has been given with the time. Now here you can see again uncoated, uncoated, the 2 points here, 2 points here, 2 points here, again one here, and then again we are following the regression analysis, or we are going ahead with the trend line in Excel sheet. We find again this is the logarithmic also. So whatever the curve, we can really analyze sometime results which are already available in literature. When we try to plot and we find that results are not matching what description has been given in the paper, so then we try to dig out the what is the real problem and why it has not been identified proper manner, and then we can do little more research on that. Here particularly we find that for unquoted case, regression is giving a much lesser compared to 0.99 in this case. In this case it is not giving that much values. That means either there is some sort of deviation in a data point, or maybe then the results which have been defined may not be 100% correct. Now we can say what are the application of the data enabled engineering. Of course, one of the major thing is the health monitoring. We will be requiring to find out what is the condition of the machine. Reason being, we want maximum efficiency, we want a minimum wear rate, and that's why we say in situ measurement is very important. Whenever the in situ measurement is required, important, we need to provide some initial formulation, initial model. That's why we require a data enabled engineering. We have a data, and then we have a already model, we have estimation, and we can compare what is the whatever the data which are coming from a sensor, it is really matching with our thinking or our logic or our model which we have provided. If it is not, then what is the difference and why it is a difference. So that's why we say utilize data to monitor access the condition of the machines, like a gear, cam follower, bearings. In almost all the big industry, they utilize this condition monitoring system. And what we want to find out the faults. We don't want a failure, so we say early detection of the possible failure should be identified. And if it is a real time monitoring, then we can really go ahead with appropriate maintenance, so the malfunction can be avoided completely. And then most of the data or most of the sensor, they don't really require a restriction, they can be go ahead with the NDT also. So that's why the measuring the oil temperature, or oil analysis, wear debris analysis, or wear debris, even the monitoring using the camera, those things are very good, and that will really help us. And based on this, we can go ahead with the predictive maintenance, because we can go ahead with the maintenance, and which will reduce the minimize downtime, and machine will not fail. Even the fault which has just started, that can be corrected, so that we can really increase the life of the components significantly. And once we have this kind of models available, whatever we have done, those can be utilized in the future for the design optimization. Because whatever we have done based on the some data available in design data book or some other book, maybe say finite element models or in the CFD analysis, we got those results, but we have modified those model using the data enabled engineering, where we are incorporating the data driven approach. Once those things are available, then we require to integrate those relation in the design process, so that we get optimized performance, because we can optimize it, efficiency and cost effectiveness. So this is very important to implement. Now we have been discussing something like a maintenance, and there's a need to define in one or two slide what is a maintenance. We say keep something in a good condition, it will be known as a maintenance strategy, or monitoring machines to identify and correct potential failure. We are using the word potential failure here, prior to event. So that possibility is that there is enough failure will occur, and then what do we do, how do we go ahead. Of course, there are a number of strategies. We say one of the strategies is a preventive maintenance, which has been utilized in industry for the years and years. Regular inspection, cleaning, lubrication, these are regular maintenance. We don't really require data driven approach for that, or data enabled engineering for that. Even the corrective maintenance, this is already known, and then there's no problem as such. However, when we are talking about the data enabled engineering or data driven approach, most of the time companies feel bad. Reason being, they assume that this maintenance is a burden on operation, and they don't want to incorporate, because maintenance cost will be 1%, 2%, 15%, and sometimes more than that also. So they assume the burden. And question comes, whenever they assume the burden, then there is a sudden failure. Let me give one example of sudden failure. You must have heard about the Bhopal gas tragedy, which happened in 1984, and where the 40 tons of the MIC was leaked into air, and there was a death of 2,500 people. Of course, more than 2 lakh people were injured or had a permanent illness as such. Now, why this has happened, and as per the one of the literature, they say that there was a refrigeration system, and then they closed the refrigeration system because it was costing something. Now, when we want to maintain the temperature the 0 degree, and refrigeration system doesn't work, naturally this will increase the temperature. So first itself, the refrigeration system which was required to maintain a 0 degree, they close the system, and naturally if there is sensor, it will give the information to us. Then because of that, MIC temperature rise, and we know that as the temperature increases of the gas, naturally leakage tendency will increase. If it is a cold, leakage chances will be lesser. And often there is a gas bubble which is trying to leak. We use some sort of the scrubber. So the volatile gas scrubber was tapped here to neutralize any leakage of MIC before escaping to the system, become a non-functional. That was also known to them. That one is that no refrigeration system, or maybe it was not in operation, it was not on. Then coming to the gas scrubber, it was also not functional. And finally, a flare, which gives information on the top that the gas is getting leaked, and because of the flare is coming out, this gives information to the people. That was also stopped. We say that flare which was used to burn off any gases that were released had been out of order for the months due to the corrosion of the pipe. Now all this can be easily monitored, and then at a lesser cost, because the cost of the sensor is coming down significantly, this can be indicated. Now if this been, maybe say one or two event, the failure of the corroded pipe was informed, or maybe the refrigerant system, it was not, suppose it was not intentional, unintentional, then it has been informed, or some sort of even the scrubber was not functioning was informed, then at least this kind of tragedy could have been stopped, or then we could have saved a number of people from this kind of problems. Now we can say every physical system, again, as a, because we have seen in tribology, um, it is a unavoidable phenomena. It can be delayed, but it's unavoidable. So we say every physical system or component deteriorate with the time. So maintenance procedures are essential to guarantee safety and effectiveness of the these systems. And then the maintenance must be carried out to ensure the risk is continuously managed once the operation has begun. So once operation is started, naturally the chances of the failure will start. It will not be zero. So it may be 0.1%, 0.2%, and we need to continuously monitor it. So during operational lifetime, maintenance should be conducted to monitor, repair any significant defect. That's what we say maintenance. And as I mentioned that often the company, if they feel it is a kind of unnecessary burden on them, and they don't want to pay any money for that. And there is a one good research publication which indicates, which was published in 2014. They examined around 183 accidents which happened in 2000 to 2011, particularly related to chemical leakage or chemical handling, processing, and storage. They found that around out of 183 major accidents, they found 44% happened because of the maintenance linking. And in addition, yeah, maybe say around 69% with a slightly different manner, they deficient planning, scheduling, and fault diagnosis. So if we want to overcome all this problem, machine learning or data enabled engineering is very, very essential. That will help in a big way. Now towards the end, I'm trying to again show the bathtub cow. We've seen that initially there will be running in wear, and that's why we use also word the infant mortality failure. And then there will be life, and this will be the residual life, or we say that of course in this case the failure rate we assume constant, but it may be slightly different. And one of the lecture I showed us 6 different kind of the failure modes, and towards the end it is a really the wearing out will occur. And now if you want to go ahead with a slightly different manner, that's why we are showing the possible failure. Initially the company has manufactured but it is not installed, so naturally it's not failing for some time. Then it comes to installation, and then IP is something where the company gives some sort of warranty, 1 year, 2 year, 3 year. They assume there will not be any failure in this duration. And after that that point, when the warranty is over, the point P is a point which at which the failure start beginning itself. Then we really require a vibration monitoring, we require a oil monitoring, we may go ahead with thermography, we may go ahead with noise monitoring, we may go ahead with the heat monitoring, or we may go ahead with any other condition based or predictive maintenance strategy. So this is a very important as such. Reason being, this is where we decided this is the functional life of the system of this one. So if the failure start from here to here, so whatever the overall life, if this has been passed in this 1, 2 and 3, say if the 1 and 2 is over, so we say remaining life is a 2, 3, or if the life has reached here, we say the remaining useful life is 0, and after that component should be replaced. However, now if with the condition based monitoring, then we may not really require this. We may go ahead with the more correction, and then we keep extending this line to this side or maybe this side. That's what we have earlier mentioned. So in this case, what we see that initial precision maintenance, which is generally done by the companies, often some companies, the sectors, they do not believe in that. Like airline sector do not believe with IP. They start directly from here itself. You say no, the first line after installation or starting, we need to go ahead. This is the overall useful life or not initial period. Of course it is subjective, and then need to really think about different manner. And we are talking this is basically a failure probability. It need to be given in terms of the probability of the failure, and we should have a statistical mean to predict that. If I want to really summarize whatever I covered, I say that in PF curve what we have shown, there are two important terms what we call as a potential failure and functional failure. And if there's a functional failure, we should stop function on the utilizing that component. However, there's a potential failure, that's a kind of indication that there is a possibility of the failure has not yet occurred, but there's a possibility of the failure, and then it is still in working condition. And that's why we really require some sort of monitoring. There's a possibility of abnormal vibration, elevated temperature, strange noise, or any other divergence from normal operating conditions. Those should be monitored. At this step, what we say, condition based maintenance is will be important, because now we are going to get a data, and that's where we can use a data driven approach particularly for that purpose. So this is very important. We also thought about something like a corrective maintenance, which is when we say that other maintenance strategies are not good, because many companies they try to compare. Condition based maintenance is naturally we require a sensor, we require a processing unit, we can require a continuous monitoring. They go with the corrective maintenance, and they say whatever the condition based maintenance cost, my system is not having that much cost itself. So what we can say, the corrective maintenance is employed only when the condition based preventive maintenance is neither technical practical or not the cost effective. As such, when the cost of the maintenance exceed the cost of the failure, so if the cost of the failure is lesser than cost of the maintenance, naturally companies will not be inclined to that side. So this is very important, and then we will continue this data enabled engineering in the next lecture. Thank you for your attention. Thank you.